Hello, my name is Pesho, and I'm a PhD student at ETH Zurich. This is a shared work that I'm going to present you today with Benjamin, Harun, André, Gunnar, and Martin, and it is about our novel optimal sequence to graph aligner that we call AStarix. Let me motivate the need for optimal alignments first. Grid alignment is a common task in bioinformatics. What is given is a reference neuron, either linear or a graph, and a set of sequencing grids. An alignment for a read is a base-to-base correspondence to the most similar part of the reference. The produced alignments are further used for a ton of applications and downstream analysis. Let me point out some practical motives for optimal alignments. The available aligners trade accuracy for speed in order to be practical, and they do suboptimal heuristics and assume technology-specific parameters. As a consequence, no existing aligner is fast and optimal. This is an issue for the trust in the produced alignments. In this work, we demonstrate that the A-star algorithm may play an important role in making the optimal aligners practical. And once optimality is in place, the discussion can start focusing more on the optimization metric that may be superior to edit distance commonly used today. Let me highlight some of the main points. AStarix is an optimal aligner, and it follows a principled approach. For each read, it finds an alignment that minimizes edit distance. It considers a shortest path formulation of the alignment problem and works equally well for graphs with or without cycles. So to align a read optimally, AStarix finds a shortest path. To overcome the need for explicitly considering every potential starting location, the reference genome is supplemented with a tri-data structure. This allows AStarix to scale to bigger references. In our experiments, AStarix scales with reference size polynomially better than any other optimal aligner. This increases if we increase the reference by a factor of 30, this only increases the runtime by a factor of 2. And this is the effect of the trie. AStarix uses A-star to find shortest paths. The A-star algorithm is like Dijkstra's algorithm, but also using additional clues about the direction of the target. The challenge of applying A-star to new domains is designing a good heuristic that serves as a clue. We propose such a heuristic function that guarantees optimality. With it, AStarix scales with noise in the reads exponentially better than Dijkstra. This result opens the way to optimal alignment for long and noisy reads in the future. Aligning to a linear reference is traditionally solved using dynamic programming. Rautiainen and Marshall generalized the algorithm to graphs with cycles. At the core is a function dp, the minimal cost to align the read prefix of length I before reaching node u. This procedure starts with aligning the first nucleotide at all possible reference locations. To align the second nucleotide, all best alignments for the first nucleotide are reused, and so on until the whole read is aligned. This algorithm is optimal, but iterates all the graph nodes for every aligned nucleotide. Therefore, the runtime when aligning a read of length m to a reference graph of size n is mn. This is too expensive for large reference genomes. So it is usually only applied for extending short reads from pre-selected locations, like in the seed and extend approach. As an alternative to dynamic programming, we consider an equivalent shortest path problem on an alignment graph. The nodes correspond to the states in the dynamic programming, and the edges are weighted by the edit operations. Assuming no negative edit costs, the problem can be solved by Dijkstra's algorithm. Unlike dynamic programming, Dijkstra may never explore some states, so those are never explicitly constructed. Nevertheless, Dijkstra will explore all nodes from the first row as their potential starting locations. These are a lot of nodes, and we will alleviate this problem using a trie. So, the best alignment can potentially start at any position of the huge reference, but we want to align reads faster than going through the whole reference. Our goal is to effectively align from all starting nodes at once. If we have an A in the read and we want to simultaneously align it to all positions in the reference genome at once, let's choose any K and collect all K-mers from the reference. Then build a trie from the K-mers and glue the leaves of the trie to the reference where they end. For example, consider the K-mer ATC here below, and also in the trie. They end at the same node. This way, the paths in the reference spell the same sequences as the paths starting from the root of the trie. Only then we add edit edges, so inexact alignments are also possible in the trie. Finally, the edit graph is implicitly multiplied by the read to produce the alignment graph. Now AStarix can search for a shortest path. Here we demonstrate why A* is potentially significantly faster than Dijkstra. This simplistic plot shows how Dijkstra explores the states in all directions. In contrast, A* relies on the estimation of the remaining distance, so it tends to prefer nodes that are closer to the target. Note how much less states A* explores before reaching the target. Knowing the direction gets you home faster. The number of explored nodes increases exponentially with trie depth. With every mismatch in the shortest path, a new layer of trie nodes have to be explored. This is the price of proving optimality, and this kills Dijkstra quite quickly. This is how A* generalization of Dijkstra behaves ideally. Ideally, there is an oracle that tells A* what is the exact remaining distance from any node. For our alignment task, we exploit the knowledge of the unaligned part of the read that is about to be aligned. The optimality and efficiency depend on the A* heuristic that is using to clue. Let's say we are traveling from Zurich to Sofia, and we are currently exploring a route through Prague. Let G be the distance from Zurich. Let H*, the minimum distance from Prague to the target Sofia, which we don't yet know. And let H be an estimate. This is our heuristic function for the remaining distance to the target. A* explores first the node with minimal sum of G and H. An estimate H that never overestimates the actual shortest distance H* is called admissible. With an admissible heuristic, the A* algorithm is proven to always find the shortest path. Dijkstra uses only G, which is equivalent to using H equal to 0, which is a trivially admissible heuristic. What does a good heuristic look like? A good A* heuristic should never overestimate the shortest distance to the target. This guarantees optimality. It should benefit promising paths, but should also heavily penalize misleading paths. This will minimize the number of explored states, and thus it will lower the runtime. Moreover, the heuristic function itself should be efficiently calculated, as it will be calculated for every explored state. Time management should not overblow the tasks that it is managing. Next, I'll present our domain-specific heuristic function. It exploits the knowledge of the unaligned prefix of the read. Suppose A star considers the state IU. It's a combination of a node and a position in the read. The first I read nucleotides have already been aligned until node U. Let G be a small number denoting the length of the unaligned read prefix that we're going to be using for our heuristic. This prefix is going to be aligned from the node U. The heuristic is simply the minimum cost of such an alignment. As most alignments are going to be terribly bad, because we're going to align them in random places, we use a branch and bound procedure to stop when the prefix alignment is bad enough. This will punish the misleading states as much as needed without spending too much resources on calculating the heuristic. This was the last piece of the algorithm, so we can now look at how everything works in practice altogether. Since A star is optimal, we are interested in computing its performance and comparing it to that of other optimal aligners. To our knowledge, there are only two such aligners, the bit parallel algorithm, which is part of the graph aligner tool, and Pascal. They parallelize the dynamic programming in different ways, but they both reach their worst case quadratic performance. This table shows runtime and memory measurements. The columns are the benchmarked algorithms, including AStarix and the Dijkstra baseline. The rows are different reference graphs, both linear and variant. What you can see is that on short reads, the trie-based shortest path algorithms are consistently faster than the dynamic programming algorithms. Another observation is that AStarix is consistently faster than Dijkstra, which we of course hoped for. What is more important than absolute numbers is how the different algorithms scale. This log-log plot shows the runtime scaling of increasing reference size. The y-axis is runtime, the x-axis is the size of the reference, and different slopes correspond to different polynomials. As expected, the dynamic programming tools bit parallel and Pascal scale proportionally to the reference size. On the other hand, both Dijkstra and A star scale with the fifth root of the reference size. This speedup is equivalent to bringing a fifth power to a linear. The memory footprint for all the alignments are scaling comparably. Here we measure how the runtime degrades with reads becoming noisier. On this logarithmic plot, this time linear on the x-axis, again, you have the runtime on the y-axis, and on the x is the number of sequencing errors in the aligned reads. Different slopes here correspond to different bases in the exponent of these linear fits. We see that with increasing alignment cost, A star becomes exponentially faster than Dijkstra. This exponent is the basis 3 for our prefix heuristic versus base 10 for Dijkstra. The study, to study the quality of the heuristic functions alone, we can directly count the number of explored states as well. The trends are almost identical, which confirms that minimizing the number of explored states is a bottleneck. The horizontal line on top marks the total number of states that is always reached by the dynamic programming aligners. The dashed line, on the contrary, denotes the theoretical minimum number of states that we are explored that can be explored by a hypothetical oracle that knows the right path. An open question is how much better could a heuristic function potentially get, and how less steep the slope can get. Let me recap. AStarix finds optimal alignments on general graphs according to eddy distance. To scale up to big graphs, we supplement the reference with a trie. To scale to noisy reads, we solve the shortest path problem with a domain-specific heuristic. It directs the A-star algorithm using the knowledge of the yet unaligned part of the read. If you are interested in our ongoing work on a novel, much more powerful heuristic for long and noisy reads, please visit poster 25 yesterday or just drop me a message. Our work continues with scaling the data structures for bigger graphs and generalizing AStarix to more practical cases. The tool and experiments are available on GitHub. For formal definitions, optimizations, and correctness proofs, please refer to our paper. Now I'm happy to take your feedback and your questions. Thank you.